Good morning to everyone. I'm speaking from London. I am an applied machine learning scientist in Zimmer Biomet, a medical device manufacturer. And today I'll talk about a subtle aspect in hypothesis testing, which is assessing if you have collected enough data for significant measurement. I'll discuss pros and cons of a few methods, both frequentist and Bayesian, highlighting one called precision is the goal. Just before I start, I want to mention that all the slides are available online, so you can follow throughout, and they'll always be there. And all the opinions are my own, not of my employer. One of my fondest projects when I started out my career in data scientist was something that I call a snail mail A/B test, which I considered both a success and a failure. I was working as a consultant for a mid-sized restaurant chain, and they wanted to see if I could bring in more new customers through the doors to their restaurants than their competing marketing firm. And I had access to all the data, and I conducted an A/B test, but it wasn't digital. They sent coupons to people's houses, and they had to redeem in store. So it took me months to get all the data back to report the results. So the success was I proved to myself and the clients that I brought in more people through the door significantly. But my main point of failure was I caved to the client's request to peak before all the data was in and to give a report. And at that stage, the results weren't as impressive. And so that was a beginner's mistake. And I definitely learned from it the fact that you really want to know when you should be stopping to report about results, so you can know if your results are significant or not. I think that's an overlooked topic in hypothesis testing, and so that's what we're going to be talking about today. I did the common thing, what I think most practitioners do, is do some power calculation and then totally forget about your inputs in that calculation when you extracted the number n to report for whoever does the budget for the experiment, and then just I wing it from there on. But there is a better approach, something that I came across reading and hearing the material from a statistician named John Krusk. You can read all about it in his book. So my main points here are taken from his chapter 13.3. I myself have been doing analysis and research for over 15 years. I started off as an astronomer, and most recently I've been working within the health sector. Two main take-home messages from today. The most common methods, both frequentist and Bayesians, something that I call a threshold stop criterion. They can yield biased results. A much better method is the focus of this talk. Precision is the goal, where the focus is predetermining what the precision should be, and then you'll get reliable results. The trade-off, of course, is it might be slightly more expensive, but then again, you'll get reliable results. So that's it in terms of motivation. I don't assume that everybody knows what hypothesis test is, so I'll give a gentle introduction to that, and then I'll talk about the main problem with the current frequentist and Bayesian methods, and I'll talk about John Krusk's precision is the goal. And I was quite excited that while I was preparing this talk and coding things up, I actually made a mistake and came across a possible improvement to precision is the goal. And so I'm very excited to introduce that as well later on. So let's start talking about what is hypothesis testing and why is stopping a critical aspect of it. Hypothesis testing is when you collect data in order to achieve a certain goal. For example, you want to reject a null hypothesis, or rather confirm your underlying beliefs. And there are many examples of that. For example, in drug development, polling data, you want to know which candidate will win. And before I talked about marketing, so you can think of A/B tests. And a very useful analogy for all these cases is coin fairness, when you have two values, success or failure. So we'll be using that throughout the demonstration today. The key challenge of hypothesis testing is that most likely you'll not be able to have a budget to probe your whole population, but rather you'll use a sample. A useful analogy is taking a sample from soup while you're making it. In our household, we like using lentils, and so those are on the bottom. So if you don't put the ladle all the way in the bottle, you'll get a misrepresentative sample, right? You might think, well, we don't have lentils. And so that you might get incorrect conclusions. And of course, the language of communicating samples is via statistics, who can tell you what to expect in terms of means and variances, etc. One of the main challenges is that stakeholders want both reliable results, but they want it fast, meaning at a minimal cost. And so that's a trade-off that every analyst has to balance. And there might be even more challenges, like, for example, clinicians might want to stop a test as soon as possible. For example, if they're looking at drug development, they want to avoid like deleterious effects as soon as possible. And so we constantly have this trade-off between accuracy and speed, and that will cause people to want to peek into their data. But the caution there is that that might result in biased interpretation. It's something that's called confirmation bias, like you'll confirm what you thought beforehand incorrectly. And so that's what we'll see manifest both in the frequentist null hypothesis significance test and the Bayesian. So by far, the most popular method is the NHST. For the reason is it's fairly easy to calculate. All practitioners are familiar with it. There are in many textbooks and software packages, but there are cons to it. First of all, it's not intuitive for non-experts. And so it does raise a lot of confusion, one of which is that with the NHST, you can only reject the null hypothesis. You can never accept it. Yesterday, actually, so one question I was most interested in is why can't the NHST accept the null hypothesis? It's stated, but nobody, I haven't seen an answer for why that is. It's beyond the scope of this talk, but yesterday I did deliver a lightning talk. So if you're interested, it's already on the YouTube channel. And I also have slides here available in which you can go through that. And for that reason, actually, if you go to the slide deck of this talk, you'll see I have all the material for NHST, but for the sake of time, I'm going to focus on Bayesian, mostly because of this reason, because the p-values, you cannot accept the null hypothesis, when Bayesian you can. To drive my point, I'm going to, like I said, focus on coin flip tests. And the reason for that, and what I'm going to look at is in sequential hypothesis testing, meaning we're going to just toss a coin over and over until we get to some threshold, and then we'll stop, or to some stopping criteria, and then we'll stop. And the reason for this is for simplicity. We're going to use Bernoulli distributions, statistics which are well defined, and you can use analytical solutions, which makes life really easy. And so what do I mean by tossing coins? Well, we'll look both at a fair coin, where the underlying parameter, the parameter of interest, is the success rate, where that's going to be theta true of 0.5, which is something that we have the privilege of knowing because we're running the simulations. In real life, you don't have access to this information. That's what you're running your hypothesis for. But we'll also compare versus unfair coin trials at 65, where they're supposed to be, where that means we're looking at something with a lot of signal. So let's first look at the at a popular Bayesian approach called HDI with rope. I'll introduce what high density interval and region of practical equivalence actually means, and then we'll talk about the results of sequential coin flipping. And what we'll see is that the Bayesian, the fact that we're doing something Bayesian, it doesn't magically correct for all the problems that there are with the NHST. And that's why I'll show like why it still might yield biased results. So first of all, what is it? The high density interval is a way of quantifying a credible interval. Like you have, it doesn't matter what the shape of your posterior is. It could be anything. And what you do is you scan from top to bottom until you get, let's say, 95% of the mass, and then you just draw the parameters of that. So that's called the HDI. And so we'll use that and we'll compare it to something that we call a region of practical equivalence. Here I'm just quoting from John Crook's book, but effectively it means take your null value, and depending on your domain and whatever you're measuring, you have to be realistic with yourself. Like, how much do you really care about differences? Do you really care about a 0.1%, or can you be more lenient between -5 to 5%? It's really domain specific, and that's what you define as your rope. what's the region that you're interested in looking to see if you're significantly beyond, because you don't really care about small, minute changes within. So that's a key aspect. So the algorithm for the stop criterion for HDI and rope is collect data until the HDI is completely within the rope, like this example, or it's completely outside of the rope, like this example over here. So in this case, we'll accept the null hypothesis. In this case, we'll reject the null hypothesis. These are actually 2 out of 6 cases. For completeness, I'll show all the 6 cases. So the 2 in which you'll reject, this is what I showed before to the right, and then you have also to the left. There's one scenario for accepting, what I showed before, if it's fully in, but then we have 3 cases in which we'll actually be inconclusive. We don't know if to reject or not. So that might suggest we'll just want to collect more data. And so that's if you're straddling to the left, the HDI straddles to the right of the rope, or straddles both sides of the rope, meaning it's too wide within the rope itself. Okay, so let's look at one example. Let's look at an example of one experiment in which we're just tossing a coin over and over. Let's say that we can go to 1,500 times. Let's say we're using a fair coin. So here this dashed line shows the ground truth. I purposely chose an example in which it starts off really negative. So everything in red means a negative toss. And this statistic here on top is the average of the cumulative sum. So again, it's binary tosses, and I'm just taking the average of the cumulative until that point. So you can see around 200, it's fairly negative. Again, it's an extreme case. And then eventually, and then it climbs up. Eventually, if you do it, very much so, like 1,000, eventually you'll get to this line over here. But of course, you have limited budget, so you wouldn't know it. And what I'm plotting down here is the x-axis is the same, it's a trial number, but here I'm actually plotting the HDI, the width. And the first thing that you notice is the width starts very large because you don't have much data, and then it starts narrowing down. And also, I plotted here the rope, so here the min value, the max value, and what you want to see in the stop criterion is where does the HDI go outside or inside, or if it's a straddler. Like over here, it's straddling, and so that's why you're collecting more data. And the first time that it's actually inside is here at point toss number 912, and so then you'll accept, okay? Then most of the time, in most algorithms, what you'll do is you'll stop the experiment then and there. But just for completeness, I'm showing what happens if you actually go beyond. You see suddenly you're inconclusive until you get a few more, and then you see you accept all the way forward, which is the correct thing to do, right? You have theta. It is a fair coin, so you should be accepting. Okay, so this is only one example. How representative is this? Well, then, so for this purpose, I ran thousands of the same experiment, where in each experiment, I stop. Like here, I'll stop at 912. I'll also briefly mention the NHST, the frequentist approach, will actually stop at 342. So around over here. The reason is because there's so many negative results, setting a p-value threshold of, let's say, 5%, that will be the stop criterion, and it would incorrectly reject the null hypothesis at 352. Okay, so like I said, that's I have a full stack of slides. I have material worth of 45 to 60 minutes, but here I'm trying to keep it short, so I'm focusing on Bayesian. Okay, so this figure here explains results for thousands of experiments like the one I showed before. So just to show like how this is representative, so I can best explain this figure, and understand this figure is keep understanding all the arguments that follow. So I'll do my best to break it down. So the x-axis is the same, it's the number of iterations, but now the y-axis is the rate of the decision being made. What decisions do we have? What we said before, we can either accept the null hypothesis, reject it, or inconclusive. The sum of the green, red, and gray is 100% at each point. And what does each point mean? So let's focus, for example, we talked about here, we stopped at 912. So if I'm pulling up 912 over here, just about, and so at 912, that means if the experiment got to 900, if your experiment stopped at 912 or before, right, it could stop before, then about 60% of the time you accept the null hypothesis at 912. Unfortunately, 20% of the time, you would have rejected the null hypothesis, and whatever is left, you're inconclusive because it's still straddling. And so this is interesting because you are doing the correct thing most of the time. You are accepting, but you can't see an asymptote here at 20%, which is very alarming, that you're incorrectly rejecting the null hypothesis. And the reason for that is that over here, we run into extreme cases in which you happen to have a whole lot of tosses that are radically outside of the rope, and he just rejected it. And so that's a main flaw with this Bayesian method called HDI plus rope. So so before we looked at a fair coin, now let's look at an unfair coin. And so here you can see it's doing the job fairly quickly. It's rejecting the null hypothesis, and it barely ever accepts the null hypothesis. And that's what you're expecting. That's what you want. And it does so after like 200 tosses. It rejects the null hypothesis. But there is still a problem, and which you cannot see over here, and what you see over here. And this figure is also crucial to understand the main arguments for today, is the fact that what I'm plotting here is a histogram of what's the sample success rate at the point of the decision. So the mean should be around 0.65 because that's the true underlying truth. But what you can see is that the mean of this distribution at 0.72. And the reason is obvious. You can see it over here, is that you have a whole lot of extreme cases on the positive side. And so that skews the results. And why is that dangerous? Because a lot of times you'll show results to a stakeholder and they'll think that, well, let's say that you happen to get a result here at 90%, and then your stakeholder will think, oh, that's representative of the sample. The sample is the result of our test is 90% likely to succeed. But that's incorrect because the underlying truth is 65%. But you ran only one experiment, and so you get one of these, for example. And so that's the main flaw with HDI plus rope in terms of you're dealing with an unfair coin. So with a fair coin, the problem is incorrectly rejecting 20% of the time. And with a fair coin, even though you're doing the correct thing, rejecting or accept in terms of rejecting, but you're likely to have a population that is unrepresentative of the ground truth. So so the takeaway from the Bayesian HDI plus rope is you can't avoid, NHST, by the way, has similar problems. And so if some people think that, oh, just do everything Bayesian, that will magically correct for everything, hence the fairies, well, that's incorrect. You won't be able to get over the main flaws of NHST, even though it does have advantages over the frequentist approach, is in the sense that you can't accept the null hypothesis, you have a much more descriptive credible interval, and you may add prior beliefs, which is beyond the scope of this talk. But my main point is it's worth the overhead to go Bayesian most of the time if you can afford it. But you can actually do better than HDI plus rope. And that's precision is the goal, which actually it's very similar to HDI plus rope, except for one key aspect is that the focus is on the HDI width, but not on its location. What do I mean by that? Well, what I mean is that what you'll want to do is you want to define how precise do you want your measurement to be? And you want to do this before the experiment. So a common practice is just take whatever your rope is and just decide like the precision around it. Normally, what's common to do is like take 80%. So that's the decision, that's the precision. And so the algorithm for precision is the goal, is collect data until the width of the HDI is smaller than the precision. Again, no mention of where the null hypothesis is. You're not adding that information when you're determining the stop criterion. And then the decision making is the same. If it's totally within, you accept. If it's totally out, you reject. And then of course, if it straddles, you're still inconclusive. So similar. Okay, so let's examine the results. So let's start off actually with the unfair coin, where here you can see that it's doing the correct thing. It's rejecting. It's taking a bit longer. Later, I'll do a one-to-one experiment comparison. You can see it takes a bit longer to get there. It still doesn't accept incorrectly the null hypothesis. But what's impressive about it is this figure this figure now. Here you can see the true rate of the mean of the sample when the sample success rate at the point of the making the decision actually perfectly overlaps with the true rate. And so that's what you expect. So that means that you can go to the stakeholder and say, hey, this is representative of the population up to some up to some variance. And so that's a great thing to have. That makes it much more reliable. But there is one main flaw that I've identified, is that so this is the main advantage of the unfair coin. The fair coin has that same advantage, except for well, I'll start with actually the positive. The main advantage for the fair coin is that it never incorrectly rejects the null hypothesis. If you remember before with HDI plus rope, we had it incorrectly rejected at 20%, but now it's never incorrectly rejecting the null hypothesis. And it is accepting the null hypothesis, but the only negative thing I can say is that it's not doing so too frequently. It's actually stopping short of 40% in the example that I chose over here. It's highly inconclusive. And so, well, what does that mean? What it shows is, well, collecting more data won't help. You'll just have to make some sort of decision based on confidence and from there on. And so precision is the goal, yields accurate results, which is a massive feather in its cap. The only black eye for improvement is that what to do when the underlying, if the null hypothesis happens to be the truth, which you don't know that, and you have to deal somehow with inconclusive outcomes. That really depends on the question and the domain. And it's a bit beyond the scope of this talk. So I was preparing this talk a while ago, and we have a newborn in our house, and she was lying on me, and I was coding up the scripts in Python, and I actually did a mistake, and it was a fortunate mistake, because I actually realized that it could slightly improve on precision is the goal, something that I call conservative precision is the goal, and because it actually it has an improved dealing with those inconclusive results that I showed before. And so I'll just present the algorithm itself, but it's actually not that too sophisticated. I'm basically taking both algorithms and I mashed them together by accident, but it actually gave pleasantly surprising results. So what do I mean by that? Well, you collect data until you both collect data until the HDI is less than precision is the goal. That's the main method we're talking about. And we have the original algorithm from HDI plus rope, if the HDI is completely within the rope or outside of the rope. So just combining both methods together, what I show here is it yields better results. So just to break it down, this might look overwhelming, but if you understand the previous plots, I'm just copy pasted them over here, where here's the new result. So just to run you by it, here you can see HDI plus rope. The main problem was with the fair coin, we're rejecting the null hypothesis incorrectly 20% of the time, and then we corrected for that with precision is the goal, but it's highly inconclusive, and with conservative precision is the goal. You can see we never incorrectly rejected the null hypothesis, but ultimately we will accept the null hypothesis correctly, just as we did here, and actually it asymptotes to 1. The main trade-off is it's just slightly more expensive at doing so. So that's if your underlying if the null hypothesis is your underlying truth. What happens if it's not your underlying truth? Well, then it's the conservative is similar to precision is the goal, and always rejecting ultimately, which takes it slightly more time than HDI plus rope, but you can see you're never accepting the null hypothesis. Well, actually, this did it, but it just takes longer. But it's worthwhile for considering this trade-off, because you don't know what your underlying truth is. One problem in all of the methods is what happens when the result is straddling, and so yeah, I don't know if there's anything one can do about that, but just make an educated guess about how to make a decision given this inconclusiveness. So it doesn't solve for it. So yeah, okay. Just to summarize, what we've been talking about today. So take-home messages is that the common methods of the stop criterion that I call threshold, both frequentist and Bayesian, may lead biased results due to sensitivity to extreme samples that might pop up, where precision is the goal, yields reliable results for the main reason that you're determining your precision in advance, so you know what to expect for. The main trade-off is it's not likely to be more expensive, and so you should budget for it, but your stakeholders will get a more reliable result, and that's what you want at the end of the day, right? Accuracy is a function of cost. There's many topics that I brushed over today I didn't look into. For example, I didn't talk about inconclusive results, how to deal with them. That's depends on domains. I didn't talk about power calculations. Again, you can like engineer this to do your own power calculations. Bayesian usage of priors, of course, is very useful. Multiple hypothesis comparisons, it has an impact on frequentists. As far as I know, it doesn't impact Bayesian. I dealt today with only analytical solutions, meaning I could use like SciPy algorithms. If you need a numerical solution, you want to use something like PyMC, again, beyond the scope of this talk, and stratification for cohorts. So just to summarize, the common threshold of the common methods, frequentist and Bayesian, of threshold stop criterions yield biased results. Precision is the goal, yields more reliable results, but at the cost of having inconclusive results that need to be dealt with. And I introduced conservative precision is the goal as a possible improvement. And so just before I finish to take questions, 2 plugins for other talks. Yesterday, I talked about, I gave a talk about causal inference and why it's a useful tool to have in your statistical toolbox, so you can get more of your data and avoid misinterpretation of your data. So I presented that yesterday. All the slides are available online. And another talk that I presented in PyData 22 is how to optimize when you have more, if you have 2 or more objectives in mind. For example, if you're comparing quality versus price and you don't know the true relationship between them, and you have scattered results like this, why is it that you should choose these as equally optimal results from which you want to subselect from? So it's a very interesting topic called Pareto fronts, and it will help you improve your decision making. Again, all the slides are available online, and actually I have a hands-on tutorial with Jupyter Notebooks. So with that, I'll thank you for your time and take questions from here.
Thank you. We have quite a few questions, but we only have time for one. I'm going to ask folks to post these questions on the Discord where the speaker can answer. Or Eyal, if you have time, you can maybe drop into the YouTube chat after this and answer these questions. Let's take this one, where the user asks, "What about the opposite question? When to know that the null hypothesis is rejected? Is there any equivalent in this framework that like to ahead of time sample size estimates? That's power of the experiment."
Okay, I'm just trying to understand the question itself. I mean, you don't know in advance if you're going to reject or if I understand the question correctly, you don't know in advance if you're going to reject or you're going to accept. That's the whole what we're trying to figure out. The objective of precision is the goal, is determining how precise you want your measurement to be, and then whatever comes. You'll have 3 decisions to make. Either you'll accept, or you'll reject, or you'll be inconclusive because it might be straddling the rope. So you don't know in advance what you're going to do. You let the data speak for itself. And just the emphasis is that if you use a standard NHST or the most common Bayesian methods, like I presented only one, HDI plus rope, you are there is a likely possibility that you'll get you'll get incorrect results, and that's what John Krusk is trying to portray with the importance of predetermining your precision as opposed to winging it kind of at the end. I don't know if that answers the question, but that's my best attempt.